Hello everyone, let us finally get to the actual material after having reviewed what game theory is and which branches it includes. We now look at non-cooperative games, which is our big first topic. And there are two main ways to represent non-cooperative games. These are not different games per se, these are different models, different ways to represent them. So the models are either normal form or strategic, and another model is extensive game. So normal form is simpler, that's why maybe it's called normal, maybe because it's often written as a rectangular array, but I do not know that. So normal form or strategic form, because here the basics are strategies, game is a three-tuple of the set of players, the set of strategies for each player I, and the set of utility functions for each player I. Where the utility function of a player, so it's a function from the Cartesian product of all the strategy sets. So it takes a strategy profile, and we often call this Cartesian product simply by capital S, and this function goes to reals. By that it gives the real utility of that player. Remember, we have proven, well, von Neumann and Morgenstern have, that it's possible to use such a utility function, and then if you have some probabilistic outcome, we can just look at the expected value. And we always use that. So that is a normal form game. Now a little bit of notation. We denote the product of a subset of the strategy sets. So let's say we look only at the strategies of players for some set Y in the set of players. Then the product of only the strategies of these players, we denote it by S subscripted by capital Y. So this is defined as simply big X, so the Cartesian product of all Si over players in Y. This is what I write for defined as. Just like the old syntax of Pascal. So basically that's one notation. Another important notation is going to be the product of all the strategies beside the given player. Because we are often going to look what a given player sees from the outside world, and he sees all the strategies besides his strategy. So we can also say that for each player I, we denote the product of J's, such that J is in the set of all players without that I. So I remove the set including I, and the product goes over all those others, and that product we denote as S minus I. So all of those who are not I. Of course, we can also denote as S subscripted by the set n minus the set, the singleton including I, but that would be a bit cumbersome, so we just use S minus I, and that's a classical notation in game theory. Now let us say anything else. Now something about finite games. A game, we assume that a game always has a finite number of players. And of course, theoretically, we can think of a game with infinitely many players, even continue many, for example. But for now, unless said otherwise, let us assume that the number of players is finite. So let me rewrite the definition of a game. It's n as i's, I in n, and the utilities for each player. Please notice that the utilities, they are functions from all the strategies of all the players. Play, by definition, depends, or at least it can depend on the action on the strategy, of all the other players. That's the meaning of this being a game, because there is interaction. So utility goes from the product of all the players, J, to the reals. Yeah, it's a very ugly R, but you understand. Let me make it better. Now, we assume that all this n is finite. We can also assume that n is at least 2, because otherwise there is no interaction if there is only one player. So it can be interesting to say what happens if n is 1 sometimes. A very interesting degenerate case. But a game is finite if not only n is finite, which is all we always assume, but if also all the strategies are finite. So G is finite if for each player its strategy is satisfied, or an equivalent condition if the Cartesian product of all those SIs is fine. Now, knowing the game by everyone, and the fact that I know that everyone knows the game, and everyone knows that everyone knows that everyone knows, and so on. In formal language, it's called this common knowledge that everyone knows the game. We call it complete information. So, definition. Now, then, what is known? That's something which can be formally defined, and there are several models of knowledge. Here we are going to take an intuitive notion of that thing, knowledge, but of course it can and should be formalized. So, known, so event is something which can happen, but it's not the only thing that can happen. Is common knowledge. If everyone knows that everyone knows that everyone knows, indefinitely long, but finite number of everyone knows, this event. Event has taken place. So that's what is common knowledge. So that for every finite chain of those everyone knows, these people know that this event has taken place, and In our case, we are interested in knowing the definition of a game, in the sense that people know who are the players, what their possible strategies are, and what are the utilities that each one of them derives from each one of the constellation of strategies. So, the game G is with complete information if the definition of G is common knowledge. Common knowledge among the players, of course. And now I think that we should just give some examples. Okay, let us look at some classical examples. Of course, we are going to see them further. The first example is Prisoner's Dilemma.